Welcome to today's paper reading. Today's paper is titled PhysDreamer, Physics-Based Interaction with 3D Objects via Video Generation. This paper was published on AR14 by Tianyuan Zhang and colleagues from Massachusetts Institute of Technology, Columbia University, Stanford University, and Cornell University. The abstract highlights the importance of realistic object interactions in creating immersive virtual experiences. It points out the challenges in synthesizing 3D object dynamics in response to novel interactions, which require understanding the physical material properties of objects. The abstract introduces PhysDreamer, a physics-based approach that uses video generation models to learn object dynamics priors and synthesize realistic responses to interactions. The approach is demonstrated on elastic objects, and its effectiveness is evaluated through a user study, showing its potential to enhance virtual experiences by enabling static 3D objects to respond dynamically and physically plausibly to interactive stimuli. The synthesis of interactive 3D dynamics is crucial for creating immersive virtual experiences. However, handling action-conditioned dynamics, which require understanding physical material properties like object stiffness, presents significant challenges. To address this, the authors propose PhysDreamer, an approach that leverages video generation models to estimate these properties and transform static 3D objects into interactive ones. Through a user study, PhysDreamer demonstrated superior motion realism compared to existing methods, highlighting its effectiveness in enhancing virtual environments. Figure 1 illustrates the process of synthesizing interactive 3D dynamics using PhysDreamer. On the left, the figure shows how prior knowledge of dynamics is distilled from a pre-trained video generation model to estimate a physical material field for a static 3D object. On the right, it demonstrates how this physical material field enables the synthesis of interactive 3D dynamics under arbitrary forces. Rendered sequences from two viewpoints are shown, with red arrows indicating the direction of applied forces. For a more detailed visualization, please refer to the videos on our project website. This slide provides an overview of related work in three key areas: dynamic 3D reconstruction, dynamic 3D generation, and interactive motion generation. In dynamic 3D reconstruction, methods use various inputs like depth scans and RGBD videos to create representations of dynamic scenes. For dynamic 3D generation, integrating 3D and video generation models is common, though current methods are limited to fixed-length videos. Interactive motion generation focuses on animating 3D objects based on user inputs and physics-based simulations, with a novel approach to distilling material parameters from pre-trained models. The problem involves estimating physical material properties for a static object represented by 3D Gaussians. Each Gaussian particle is characterized by its position, opacity, covariance matrix, and color. The primary goal is to estimate fields for mass, Young's modulus, and Poisson's ratio to enable realistic interactive motion synthesis. Among these, Young's modulus is crucial as it determines the object's response to forces, with higher values indicating stiffer materials and lower values indicating more flexible ones. This modulus influences the rigidity and frequency of the object's motion. Figure 2 illustrates the effect of Young's modulus on the motion of a simulated flower under the same external force. The figure shows three flowers with different Young's moduli: 1 times, 10 times, and 100 times. The flower with the highest Young's modulus, 100 times, exhibits smaller oscillations and higher frequencies, indicating a stiffer material. In contrast, the flower with the lowest Young's modulus, 1 times, sways the most and oscillates at the lowest frequency, demonstrating a more flexible and elastic behavior. Time annotations below each image indicate the duration of one complete motion path shown in the figure. PhysDreamer's workflow begins with rendering a static image I0 of a 3D scene. An image-to-video model is then used to generate a video sequence, I0, I1, ID, depicting the object's motion. The core of PhysDreamer involves optimizing the material field E, x, and the initial velocity field V0, x, using differentiable simulation techniques. This optimization is performed using the material point method, MPM, integrated with 3D Gaussians to ensure that the rendered video closely matches the reference video. The optimization process is further refined by parameterizing the material and velocity fields, applying total variation regularization, and splitting the optimization into 2 stages for better stability and convergence. Figure 3 provides an overview of the PhysDreamer system. The process begins with an object represented as 3D Gaussians, which is then rendered from a specific viewpoint. An image-to-video generation model is employed to create a reference video showing the object in motion. The system uses differentiable material point methods, MPM, and differentiable rendering to optimize both a spatially varying material field and an initial velocity field. The goal of this optimization is to reduce the difference between the rendered video and the reference video. The dashed arrows in the figure indicate the flow of gradients during the optimization process. Figure 4 illustrates the process of accelerating material point method, MPM, simulations using k-means downsampling. Initially, k-means clustering is applied to create a set of driving particles at the initial time step, t = 0. These driving particles, represented in yellow, are the only ones simulated. During rendering, the position and rotation of each particle are determined by fitting a local rigid body transformation using the neighboring driving particles. This method significantly improves simulation efficiency by reducing the number of particles that need to be simulated, while still maintaining the accuracy of the rendered results. The experiments were conducted using 8 real-world scenes, each captured with multi-view images and 4 interaction videos to illustrate natural motion. The baselines for comparison were PhysGaussian and DreamGaussian 4D, both initialized with the same strategy as our approach. The evaluation focused on the quality of synthesized object motion through a user study using the 2 alternative force choice, 2AFC, protocol, involving 100 participants who judged 800 samples. Figure 5 illustrates the interactive synthesis of 3D dynamics. On the left, the visualization of material fields is shown, where brighter colors indicate higher Young's modulus within each example. On the right, an external force, represented by a red arrow, is applied to each object. The subsequent columns demonstrate the object dynamics as rendered from a static viewpoint. This figure effectively showcases the application of material properties and external forces to simulate interactive 3D dynamics. Figure 6 presents a comparison of our PhysDreamer results with real captured videos, PhysGaussian, and DreamGaussian 4D using space-time slices. The vertical axis of these slices represents time, while the horizontal axis shows a spatial slice of the object, denoted by red lines on the object column. These slices effectively visualize the magnitude and frequencies of the oscillating motions. Both our PhysDreamer and PhysGaussian results are simulated under the same initial conditions, providing a clear contrast in motion realism and visual quality. Figure 7 illustrates the comparison between single-view and two-view supervisions in optimizing the material field of an object, specifically in alocasia with self-occluding structures. The top section of the figure shows the results from single-view supervision, which provides less effective supervision signals for the materials of occluded parts, as highlighted in the blue boxes. In contrast, the bottom section demonstrates the benefits of using two-view supervision, which allows for a more comprehensive optimization of the material field. The spacetime, XD, slices in the figure visualize the vertical axis as time and the horizontal axis as a spatial slice of the object, aiding in the understanding of the magnitude and frequencies of these oscillating motions. Table 1 presents the results of a human study using a 2AFC, 2 alternative force choice, method to compare PhysDreamer, our method, against real captured videos and 2 baseline methods, PhysGaussian and DreamGaussian 4D, on 2 criteria, motion realism and overall visual quality. The study involved various materials such as alocasia, carnation, hat, and different colored roses, orange, white, and red. The results indicate that PhysDreamer is preferred over the real captured videos and both baseline methods in terms of motion realism and visual quality. Specifically, 80.8% of participants preferred PhysDreamer over PhysGaussian in motion realism, and 65% preferred it in visual quality. The table also highlights that since the static scenes are identical, the visual quality is influenced by the generated object motion. In this work, the authors introduced PhysDreamer, a novel approach for synthesizing interactive 3D dynamics by endowing static 3D objects with physical material properties. The method leverages object dynamics priors learned by video generation models to estimate spatially varying material properties, enabling realistic physical interaction with 3D objects. Experimental results demonstrated that PhysDreamer significantly outperforms state-of-the-art methods in terms of motion realism, as validated by a user study. However, the approach has limitations, including the need for manual object specification, computational demands, and a current scope limited to elastic objects without collisions. Future work may focus on improving efficiency and expanding the scope to include more complex interactions. Thank you for watching.